In this video lesson, we're going to take a look at the periodic table and the modern grid system that it has in it, and also how metals and nonmetals are different from each other. So if you would please, we want to have our notes out as we're going through this, and we're going to actually kind of fill in those notes as you do it. So probably the best way is to get my video into one screen and then have the notes on your second screen or as a dual screen on your iPads. Okay. So first of all, here's our modern periodic table. One thing we will notice that it comes in 18 different columns. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 18. So those 18 columns, we give them the name groups. Okay. So whenever from moving forward, I won't call them columns. I'll say this is a group 1, this is a group 13, this is a group 17. So group means columns. We also have 7 rows or 7 periods. Okay. What this does for us is anybody talking about the periodic table can very quickly identify the location of an element, because you can say, well, where is oxygen? Well, oxygen is in group 16, period 2. Okay. Or what element would be in group 2, period 4? Well, that would be calcium. Okay. Or what element is in group 10, period 6? So we go over group 10, go down to period 6, and that'd be platinum. Okay. So it's a grid system that we can then use to talk to each other by groups and periods. Okay. So as you look at this, just make sure that you remember that groups are vertical columns and that your rows are your periods for your system. Okay. Now, you may wonder, well, why is it so like Y1 drops down 2? Why does it dip down and stick up, and what pulls down here? We'll get into that as we kind of go through, but right now our basic organization is that grid of 18 by 7. Another way that we organize the periodic table is we actually have a segment of the table that's all metals. We have a segment of the table that's all nonmetals. Okay, so one of the big distinguishers of what an element is whether or not it's metallic in nature or if it is non-metallic in nature. Okay, so there's a reason why on the periodic tables that I handed out to you, and maybe you actually had those tables in front of you. In fact, if you had those tables in front of you, you maybe would want to label this also. Is there's this stair-step line where it starts here between boron and aluminum, and it stair-steps down in this corner of the periodic table. Now that stair-step line separates the metals, or all the elements that act like metallic, versus all the elements that do not act like they're metals. Okay, and then we have a few of them that sit on that line that we kind of shade in purple here. We call them metalloids. They're kind of like in between. So they're not metals, they're not non-metals, but they have a little bit of both in them. So it's kind of like a phase or kind of an area in here that they're kind of transitioning from one to the other. Okay. It's also worth noting that if we go over here, that stair step will continue over, and then hydrogen, number 1, way over here is not a metal. It's considered a non-metal also. Okay. So any elements in this area here that's in green are all our metals. These orange ones are our non-metals, and anything on that stair-step line are our metalloids, is how we term the terms for those. Okay. Now, those metals, non-metals, and metalloids have certain properties to them. Okay. So if we take a look at ways that we can distinguish between them. So what makes a metal, and what makes a non-metal a non-metal? Okay. So the first thing is, and the very best way to distinguish this is conduction. Okay. So we're talking about conducting heat or conducting electricity. They both work the same. Okay. So if you're a metal, you are a very good conductor of heat and electricity. Okay. That's why we use metal pots for cooking, so they can conduct heat really well that way. It's also why we use copper and gold and other metals to conduct electricity, because they're really good at conducting electricity, whereas our non-metals are not good at that. Okay, so we say that non-metals are very poor conductors. That's why we see things like carbon and silicone and some of those other things that we don't use for conduction that actually help us as being more of an insulator versus the conductor. Okay, now if you're a metalloid, you would sit on that stair-step line, and you'd be considered a semiconductor. Semi meaning partial or kind of in terms of our conduction. So metals are very, very good at it. Non-metals are very, very bad at it. And those things that are on that line, they're okay at it, okay, in terms of what they are. In fact, the absolute worst metal at conduction is still 100 times better than the best non-metal. So that's how big a difference there is between those two things. Okay. Next thing that we want to take a look at is what happens if we put it under stress. Okay. So if we stress a metal by pushing on it, pulling on it, trying to like change its shape, will it do that? And metals will. So metals are considered to be malleable and ductile. Those are two terms we use for them. So basically we can shape them or make them into wires. So if you think about it, we take metals and we bend them and shape them in lots of things to make fenders for cars, to make pans, for all kinds of attachments and levers and machinery. So we're always shaping metals because they have that ability. Where non-metals, we don't do that, okay? Non-metals tend to be very brittle and they tend to crack really easily, okay? So if you take like charcoal or carbon and they crack really easy, sulfur breaks really easy. So our non-metals are going to tend to be what we call brittle instead of being malleable and ductile. So brittle meaning that it can break or crack if you stress it or if you put it under stress, okay? Now metalloids, they're kind of variable. Kind of depends on which one they are. So there's not a really great data on metalloids for that. The next comparison we're going to do is luster, okay? So luster is how shiny it is. So can you polish it into a shine? And metals have high luster. So if we take a metal like copper or aluminum or gold or silver or any metal really, and we polish it and use sandpaper on it and then get it nice and smooth, it's going to shine for us and creates a really cool luster. Non-metals won't do that, okay? So even if you try to polish them up, they're not going to create this luster. They're going to stay very dull looking or have no shine to them, okay? Now, we already know this because we already know how charges work, but our metals are going to form ions and they're going to lose electrons, okay? So if you go back to our ion stuff from our last unit, where we talked about positive ions and negative ions, all of the columns or all the groups that were on the left-hand side of the periodic table, they were all forming plus charges. So plus charges mean losing electrons, okay? And all nonmetals will gain electrons, okay? So we could maybe remind ourselves by saying like this is a +1 or a +2 over here or a positive, and these would be negative because we're going to lose the electrons. So all metals become positively charged, all nonmetals become negatively charged because they gain electrons. Okay. Now, at room temperature, how do we normally find metals? Well, they're usually solids. Okay. Almost all of our metals are solid at room temperature. Mercury is going to be the only one that's a liquid at room temperature. Everything else is going to be a solid at room temperature. Okay. Non-metals are really variable. Okay. So non-metals can be anything from a solid, liquid, or a gas at room temperature, but most are gases. Okay. So at room temperature, most of the time we're going to find our non-metals as a gas state. Some notable exceptions are phosphorus, sulfur, and carbon. Okay, so those three things that we use kind of a lot. You've heard of sulfur before, probably. Carbon for sure, you've probably heard before, and maybe even phosphorus. Those are solids at room temperature, but for the most part, they are gases at room temperature. Side note, the only liquid at room temperature that's a nonmetal is bromine. Okay, so mercury is the only metal liquid, and bromine is the only non-metal liquid at room temperature. Now, all of our metalloids are going to be solid at room temperature. Okay. Now, for metals, in terms of how those electrons move, they have freely moving electrons, which means inside the metals that they can move around anywhere they want to for those electrons. They can slide past each other. They actually can slide from one atom to the other atom that they don't really care. Those electrons are able to move. For nonmetals, the electrons aren't able to do that. They're kind of locked in place. In fact, this is the reason why of the good conduction and malleability ductility. So because of the free moving electrons, these two other properties actually exist, this conduction and malleability. Because nonmetals have locked electrons, they don't conduct well and they end up being brittle in there, okay? And then for our metalloids, they're partially free. So because they're partially free, we get partial or semi-conduction in them, okay? So that's a good comparison between these three major categories of elements in our periodic table. We're going to dive a little deeper into the metals themselves and kind of how metals work, okay? So for metals, when they form, they actually form what's considered a loose crystalline structure, okay? So if you look over here, we see kind of these crystalline structures that metals form. They are crystalline in nature, and they're kind of has that kind of metallic luster to them that you'll see, but there is a pattern to it. So there is like square and rigid shapes and that stuff. So there is crystal structure to metals, okay? There is no chemical bond between them, okay? It's just metals attaching to themselves. That's all they are, okay? So as a result, because of this crystalline structure, because they build structure inside them, they get a higher melting point and more luster than nonmetals, okay? So another thing we could say about metals is that their melting point is going to be higher than that of nonmetals, which makes sense because they're solid at room temperature, where most of our nonmetals are gases at room temperature because they've long since melted, and not only melted, but they've also boiled off and now are a gas, okay? Here's a quick little video of showing metals crystallizing on the surface here. So you kind of see this here. You're going to see them kind of growing and crystallizing here. And now this is zoomed in. So we see that metals, as they form, do form kind of a crystalline pattern to them, very much like other ionic compounds would, where nonmetals would not form that kind of pattern. Now, let's talk about metal conduction. So metals are good at conducting, okay? So let's talk about first electrical conduction and heat conduction. Both are very similar to each other, and the idea is that if you want conduction, or the ability to move electricity down a wire, or to move heat down a wire, you need to have electrons that are free to move, okay? So that means the electrons inside a metal actually are not attached to the individual nuclei. Instead, they kind of overlap each other, as we see here in this image, okay? So these electrons that belong to this atom, because they're overlapping, it's kind of like a playground where you can run from one spot to the next, okay? So imagine maybe like an apartment building, where you can run from one room to the next, or maybe like if you live in a neighborhood and there's no fences between your yards, and as kids you would play in one person's yard, then you'd play in somebody else's yard, you go play in somebody else's yard, you go play in somebody else's yard. Because there was no fences, you could just run between whoever's yard you wanted to and get where you wanted to through to the neighborhoods, okay? That's something we did all the time when I was a kid. We would start at my one friend's house, and we would go see our other friend. Well, he lived way over here, so we didn't want to go on the street, so we would just cut through people's backyards. They didn't always like it, but we would. And we could just kind of weave our way between backyards because not many people had fences where I grew up. And electrons kind of the same way. So these electrons can kind of just freely move wherever they want to inside of these chunks of metal, okay? And they're going to randomly move. Some will go left, some will go right, some will go up, some will go down. It doesn't really matter. Okay, so we call that a random movement because of the electrons are moving freely. Okay. However, if we attach a power source to these metals, so if I hook up an electrical wire and have a negative side and a positive side, what I can do is the battery can actually push the electrons all in one direction. So that's how like batteries work in your phones, is they take these free moving electrons and they push electrons in one side and they force them to run across the wire to the other side. And these moving electrons all in the same direction create current. And that current is what runs your phone. It's the electricity that runs your phone, is this patternized or this continual movement of electrons through the circuitry of your phone or your computer or your iPad or your light switches, or your toaster or your refrigerator. They all have this movement of electrons, and that movement of electrons then powers that device, okay? Without the battery source, electrons are going to move randomly and not do anything, but we control that by hooking a battery or plugging something into an outlet to make those electrons move the direction that we want them to, creating power or creating electricity, okay? And we call that flow or current as we do it, okay? So metals are really good at conducting because of the overlapping energy levels or overlapping clouds that we talked about before, okay? It also is allowed for metals to be very malleable and ductile because, again, they have these overlapping these energy levels. So if they hit each other or slide, they can actually slide past each other, okay? So because of the free-moving electrons, where the electrons aren't locked in place, because there's no fences between each atom, like we said, they can slide past each other, and they can change shape and be molded. That makes them malleable. It also makes them to be able to be ductile, okay? So in the manufacturing world, we have things called presses or forging, where we can take a hot metal and we actually can press on it and it can reshape it into new shapes or forms. Okay, it's called forging. Okay, there's hot forging, there's cold forging, there's all kinds of different types of forging. But the whole idea is the same, is that the metals have the ability to be reshaped without cracking or breaking, and we can create the shapes we want. Okay, we also can take things that are thick, and if we pull on them, we can actually have them spread out. Have you ever done that with like taffy or your gum, where you take it and you pull on both sides and it like pulls apart, and then it takes a long time before it finally breaks? Well, that's called being ductile. Okay, so if you're ductile, you can actually be stretched out before you snap or break. So things like taffies or gums that are like that too. Now, they're not metals, but they have the same properties of what they are. So if we take Thor's hammer here and we allow it to hit these metals, that's going to be able to slide past each other. Notice how it doesn't crack or break. It just creates a dent inside that metal. Same thing would happen in your car. If somebody door dinged you, or maybe someone hit a golf ball and it hit your car and it left a dent, or maybe hail hit your car. What happens is that object hits so hard, it literally pushes the atoms in of that metal and it leaves a dent inside there. It doesn't break anything. They're still there. But then if you want to push them back, you can, to reshape that. So that's one way like paintless dent repair works, is you got to push it in. So someone just comes on this side and they push it back and they actually fill that space back in terms of how the atoms slide with each other. Okay. Now, we have 4 different special metal groups. We have the alkali metals, the alkaline earth metals, the transition metals, and the intertransition metals. We're going to talk about each one of these groups independently, but not for this video lesson. So we're going to stop here. Thank you.